So this question got asked earlier today about one of the things you actually had to draw. Which question was this you had to draw? Okay, it's the first question on the Unit 2 review, and it asks you to draw the solutions of magnesium chloride dissolving in water, correct? Is that how it's worded? Let me look at it specifically. Explain. Okay. So number one, draw a molecular level picture for the hydration of 3 formula units of magnesium chloride. So let's start with that part of it right there, because Peyton, a little bit of what you have is a little off, I think. I'm not sure. I hadn't counted them up yet. But it says three formula units of magnesium chloride. Now, first of all, what is magnesium chloride formula? MgCl2. I want to kind of take a side step, and I want to talk about this right here. This right here is the same thing as this word. But this word is used for what type of bond? Molecule is a covalent bond. So what I just need you to understand is when you see the term formula unit, it is only applying to an ionic bond. So it's the same concept. It's just that you need to know if you do see formula unit, it is specifically referring to ionic. The word molecule is specifically referring to covalent. So that may kind of help you adjust that. So then it says specifically 3 magnesium chlorides. So then it also says the hydration of. What does hydration mean? Adding water to it. So my question to you is, if I put water on magnesium chloride, will it dissolve? How do you know that? Solubility rules. That's really the answer. So chloride will be soluble unless it's with, don't say that, silver, mercury, or lead. Okay, you can know heavy metal bad guys, but there's a lot of heavy metals up there. Okay, make sure you know silver, mercury, and lead. So when it says 3 formula units of this, you need 3 of these, which would be 1, 2, and 3. So Peyton, again, like I said, I have not counted yours, but when you draw this, how many magnesiums would you have in solution? You'd have 3. How many chlorides would you have? 2, 4, 6. So you should have twice as many chloride ions as you have magnesium ions, right? Okay. Now, so Peyton, like I said, let's go back and let's actually count yours. You had 1, 2, 3, 1, 2, 3, 4, 5, 6. Good, you got it right, okay? Very good. Not that I didn't trust you, but like I said, I didn't count it. So that's how you would do it. The next thing, and like I said, she didn't finish, she was drawing this. Whenever you draw water around a molecule, and I told her this, last year, a question on the free response had them to draw a hydration of a solid compound. They actually used calcium chloride, which is interesting because it would just be Ca2 plus in this rather than the chloride, rather than the magnesium ion. But the second part that you need to know is the orientation of the water molecule. What's important about the orientation of the water molecule around these ions? Okay, which part of the water faces the cation? The oxygen must face it. So that's why you notice she's got the red oxygens facing all the magnesium ions. Now, specifically in that question on the test, it said draw 4 water molecules. But again, for me, 3 is okay, but I want to start adjusting it because normally when you see it one year, it slowly becomes a trend. So remember, is it just 4 around this thing, or is it engulfed completely? I mean, you could draw moles of these things around them, but they just kind of want to make sure that you know the 4. So if oxygen is surrounding the magnesium, what part of the water would be surrounding the chloride ion? Why? Chloride's negative and hydrogen is positive, so it's going to do the opposite attracting, okay? That's part number 2. So the first part was making sure you had the right number of each ion. The second part was making sure the water molecule was oriented correctly. And the third part, that's probably the one that we leave out the most, is the size differential. It's called ion to charge ratio, or size to ion ratio. And and I showed you this picture. Some of you probably don't even remember it, but I showed you this. I think this is when Nick turned into a jerk and I had to stop teaching Because I was explaining this slide, and I said, "You're why I hate teaching." I actually remember that specifically. Yes, it had everything to do with this because I said if I take you up to Slingliff and I lay little Johnny outside, you said something about murder him or something like that. I remember that specifically. That's how mad you made me that day. It wasn't a positive reflection. I don't either. But here's the deal. So I need you to understand, whenever something turns into a cation, it becomes smaller. Okay? And again, the reason why is because A, you're losing an orbital. It's dropping one of its shells because it's becoming more stable. And also, what was the word that I wrote up here? I wrote Ze. Because if you're trying to contain, in the case of magnesium, if you're trying to contain 12 electrons with 12 protons, do you agree that's a 1-to-1 ratio? Well, what happens when you lose 2? Now you've got 12 protons pulling on 10 electrons. Now you've got a higher ratio to pull those electrons in even a little bit closer. So that is why cations get smaller. And I'll cut your question in just a second. But then the X, the chloride ion, it had 17 electrons, and now it added 1. So it went up to 18. But you still only have how many protons? Only got 17. So that's like adding one more kid to the playground and you having to watch that one extra kid. And he's the worst kid on the playground. It's allowing him to escape a little bit farther. So anions grow. Answer. That. Okay. Those of you that can't, go ahead. Sure. No, and that's what you kind of missed. And I want to go back, and those of you that came in late, I want to show you this. The question specifically said draw 3 formula units. Part number 1. Formula units stands for ionic. We've always known molecule is covalent. This is just a new phrase. So if you ever hear the term formula unit, it is specifically and only referring to ionic. And it said 3 of them, which means you had to have 3 magnesiums and 6 chlorides. I will tell you this, they will never make you draw that many ions. At most, it would be 2, never 3. Yes, ma'am. Thank you for drawing that, Peyton. All right, let me ask you this. What is a molecule? It's a covalent bond, okay? Molecules, such as water, are a little easier to draw than some of the larger outlandish molecules. The way that you would more than likely be drawing a molecule is by its Lewis structure. The Mickey Mouse looking things are waters. Yeah, she didn't finish. And that's what, say it again. Yeah, and so, like I said, she didn't finish it, so I'll kind of help finish it off for her. The 4 was what the question had had last year, so it is a little bit easier, isn't it? Yeah, but like I said, she didn't get to finish the other ones, but she would put the hydrogens facing. So you've got the water there, and the water there. I've learned that over the years. Just make the pen size bigger. It makes it a lot easier. Yeah. Okay. Yes, sir. Up there by the bus area bathroom. Yeah. Good luck. You may be there for a while. Okay. All right. So we good on this question. Do you agree there's a lot involved, but it's very specific? Yes, ma'am. Okay, that's a good question. That's one thing I want to cover, but I want to say it again, okay? Magnesium is what charged? Guys, magnesium is what charged, Mary? 2 plus. What do opposite signs do? And what do we know about oxygen's charge? It's partially negative. So the oxygen is going to face the positive, and then over here, the hydrogens are partially positive, so they're going to face the negative. Okay. So, and again, you would have earned a point for drawing the orientation of the water correctly around each one. So now do you see what I mean? How they would never require you to draw that much? Because think about it. If they said draw 3 formula units and draw 4 water molecules, they would have to count every single one of those for every single test for every single student that took it. That's a lot of counting. So, handwrite? Oh, absolutely. It takes them, I think, 5 or 6 days at 8 hours a day of straight grading one question. I mean, Yeah, because what they do is they become experts of that one question, and so they see trends within the question, and so I mean they're probably grading a test every 6 to 8 seconds. That's how fast they're going through it. Oh yeah, it's you have no clue how tight their restrictions and guidelines are. Big, and they take you. No joke. Hang on. All right, so number 5. Guys, y'all listen. Determine the mass needed to prepare the following solutions and explain how to create the solution. Again, you didn't. All you had to do was explain it for A and B. You didn't have to do C. So the first question is determine the mass needed to prepare the solution. So if I need 225 milliliters of a 0.330 molar potassium nitrate solution, I've got to find the mass out of that, right? Yeah, I'll come back to C, but let's do this one first. No, I'm going randomly. She's asking me to do them randomly. I will come back to that. Remind me to do it next. So the first thing is they say um, we need 225 milliliters of a 0.330 molar KNO3 solution. This is 5A. But then the question specifically says determine the mass. So the question is the mass. Now I'm asking Peyton this and Peyton only. Based on the data that they gave us, can you possibly even get to the mass? What's your first thing you have to do? What's the only way I can get to mass? What? I've got to get moles and then I got to get grams. Now my first question is simply based on the values they gave you explicitly. Nothing else, just those two numbers. Can you find the moles directly from those two numbers? Those two numbers. Very good. That's the question I'm asking you. Don't forget that this has to turn into liters because moles is equal to molarity times liters. Okay? Milliliters times millimoles would equal moles. No, milliliters times millimoles would equal millimolarity would equal moles. I think. I see. That's why I don't like it. I hate it. All right. So this should give me a certain amount of moles. Anybody have that? Okay. So I've got that many moles. Now, yeah, that's KNO3. But then I've got to convert that to what? Grams. All right. And 1 mole. How many? What is the mass of potassium nitrate? I really wish I had my calculator. I know, but I need a graphing calculator. Nick, please stop screaming. 101. Okay. 101.11. And then that should give you how many grams? I mean, he says it's right. It's 39.99. Isn't it? What is potassium? Okay, my bad. 30. Shh. Okay, here we go. No. Potassium is 39.1 plus 14.01 plus 16 times 3 is 101.11. You got it right. Times 0.0743 gives me a mass of 7.51 grams of KNO3. So that technically answers the question of what mass would you need. And I want to go ahead and I want to talk about this. And I'm not going to write all of this down because you need to go back and you need to look in your notes of how to explain how to do this. Okay? Because that's all we've worked these out. And I'm telling you, you're going to see either a solution or a dilution word problem of explaining. You're going to how to do it. So the first thing you would do. way too late for that. Okay? The first thing you do is mass out 7.51 grams of potassium nitrate and put in what size what? What size? Very good. A 0.225 liter or a 225 milliliter. Now, Sarah, let me ask you something. It's more than likely going to be better to use what they gave you first, but you can use that if you want to. This is a lot more appropriate. So 225 milliliter what, Devin? Volumetric flask. Okay? Now, are you just going to take water and just dump it in there? No, okay? Place enough, what? Warm, hot, distilled water to dissolve or swirl, practically dissolve, that's a good word, swirl, stir, whatever, to dissolve it, and then what? Fill it to the mark on the neck, okay? Which, and again, if you want to go that one extra step, you can say to produce a 0.33 molar potassium nitrate solution. Again, the more details, the better of accuracy you'll be. Yes, sir. That is your homework for this chapter. Yeah, I mean, we're working through some of these problems, yeah. Yeah, I mean, that's fine. No, I mean, you should have already done it, but okay. Kinda, but a lot more detail. You have Friday and Saturday. Not my fault. You have Friday in class. All right, Kennedy. Shh, guys. Yes, ma'am. Yes. So, to answer your question, Kennedy, there is a side that you have to put the electrons on. If it's the oxidation side, the electrons go on the other. And what I mean by other is it means they are a product. If it's a reduction half, the electrons are reactants. Because think about it from this perspective. If we look at it from this, oxidation is a what? A loss. Think about this. If you lose something, are you going to produce that as a product? Are you going to get rid of it? Are you going to lose it? Yes? So a loss has to be given off as a product. But what is reduction is a, which means you must add it in to you. Well, if you put an electron as a reactant, aren't you going to gain that? You're going to put it in, it's going to be a part of the product. It's not given off with a product. So if you look at it from molecular atomic structure wise, this is what's physically happening. This red part is just a mnemonic. Okay? I don't know. But the one thing that I do want you to remember, since we're on this topic, one compound can go through both oxidation and reduction. We worked a problem like that. Make sure you understand that. Okay, hang on. You had another one. Go ahead. All right, say that one more time. So are you asking what the charge is -4? Yes, the charge is -4. No, she's asking specific questions about something else. I agree. Yes, sir. Okay, say that one more time. In an acidic solution, yes. Okay. What I'm telling you is whenever we get into electrochem, there are going to be some redox half reactions that are going to tell you that this is in a basic solution. In a basic solution, you should have no hydrogen or hydronium ions. Because what is pH? pH is the calculation of how many hydrogen ions you have. Okay? Well, if the pH is above 7, which means you have a basic solution. Well, hydroxide is the presence of making it a base. So if it's a basic solution, you have to have hydroxide ions. I'm not teaching you yet how to convert it from an acidic solution to a basic solution. That will be later. So just know that if you have a hydrogen ion and it says acidic solution, it's okay. You don't have to cancel it out. But when we get to basic solutions, you're going to have to get rid of that hydrogen. You can't leave it in the final answer. Okay? All right, Chris, you had a question? Speaking of that, Chris, come here for a second. It's okay. Okay, what about it? Oh, yeah, the oxidation state, it was 5/2. Yeah. Set it equal to -2. You've got -2. You've got -8. You've got to have +6. No, is that right? No, that's not right. That's -12, which is +10, and 4 divided by 10 is 5/2. Okay, but holy crap! Seriously. So, Chris, the interesting part about you bringing this up, this is not the entire reaction, but there's actually a yield here, and this is the product being formed, right? So here's the point that I want to bring up to you. If you solve for the oxidation on this one, which is -6, which is +4, which is +2. So let me ask you something. Does sulfur's oxidation state change? Does it go up or does it go down? It goes up. So what is this? This is oxidation. It's weird, but if you go back and look, I promise you. Matter of fact, let me see if I can find it real quick. There is a slide in here that says specifically irregular. Come on, it's right here. Hold on. Okay. Right here, specifically, Chris, it says, beware, there can be non-integer oxidation states like this, where iron's charge or oxidation state is 8/3. It's possible, it's just really rare to see it. And that compound is just one of those that it happens to have a 5/2 oxidation state. All right, Devin. Okay. Okay, what is it? The oxidation state of a metal is its charge. Yep. No, I mean, it's just a mnemonic device to help you remember what oxidation and reduction are. Oil rig. Oxidation is a loss, reduction is a gain. Leo says GER. Losing electrons is oxidation. GER. Gaining electrons is reduction. That's all that means. That is a great question, and I do not have a knowledge to tell you yes or no on that. I would assume they have to if these are real compounds. But how, I don't really know. Yeah. Okay, when you're doing redox reactions, remember if you've got the ox and raw half, like I said, just coming over here to remember. So you've got, remember you always have to have the atoms balance, you always have to have the charge balance, and you always have to have the electrons equal. Does that help? Okay. Are any other problems you guys want me to do? All right, actually, let's go back real quick. I said let's do this earlier, and I didn't do it. Number 6C, and I don't know if I still have this up here or not. No, it's all been cleared out. But the problem we did this morning was we tried to dilute a 6 molar nitric acid to 1,200 milliliters of a 0.025 molar nitric acid. And then part C, it says explain the procedure you could use to prepare one of these two solutions. So again, we went from a 6 molar nitric to 1,200 milliliters of a 0.025 molar nitric. And so remember I wrote over here on the left, I said when it says dilution, what was that little help that I gave you? No, in blue, I wrote it there to the side. Whenever you see add water, makes the higher concentration less concentrated. Okay, that's what all dilution is. Adding water makes the higher concentration become less concentrated. So we're taking 6 molar and we're going to convert it to this stuff. But we have to add water to this 6 molar. But the first thing you have to find is what? You have to find the milliliters of your stock, right? So we did MS/VS equals MD/VD. And what was the milliliters that we found? Should have been 5.00, right? So, and the question was, how much water did you have to add also? Yep, it was 1195 milliliters of H2O. So now I want to go back and I want to make sure you remember exactly how to do this. This is actually a great question to ask this on because, first of all, how big of a volumetric flask should you end with? 1200 milliliters, right? So what we're going to do is we're going to start, this is a huge flask, okay? So this is a 1200 milliliter volumetric flask. And you're going to put in how much base, or how much 6 molar? We need 5 milliliters of 6 molar nitric acid, right? But here's the reason I'm asking you to answer the procedural part to this. Can you just dump all the acid in and then pour the water on top of it? How do you mix acids and water? You add acid to water. What happens if you pour water on acid? Wah. Okay? So always add acid to water. So what does that mean you need to do? Do you add all 1195 milliliters first? That would be a pain in your back rear bone. So what could you do? How could you explain this? Add about half full first. Halfway, fill the 1200 milliliter volumetric flask approximately half full of water. You could say 600. Approximately is because if you say 600, is that leaving you any wiggle room? No, you can say approximately halfway full. That gives you some wiggle room because you can eyeball half full, right? Okay. Then, so actually, let me change my colors here because it's a lot easier. It'd be a lot better if I use that. So we've got approximately 600 milliliters of H2O. Then what would you add? Your 5 mils of 6 molar. Does that make sense? And then what would you do? Yep, and you'd fill it up. So then you've the rest of the way with water. And then when you're done, what have you produced? That solution that it asked for. Now, you only add water first when it's a what? An acid. If it's a solid, do you just dump the solid in and pour water in on top of it, stir it? Yep, that's fine. That's perfectly fine. Okay, but only water in first when it's an acid. Is that cool? All right, hang on. Kennedy, you wanted me to do another question earlier, didn't you? All right, Kennedy, fine. We'll come back. All right. So let's look at number 7. It says a 0.0544 molar solution of iron 3 bromide. So let's start there. What is the chemical formula for iron 3 bromide? Okay, iron 3 bromide is added to 0.08750 molar solution of sodium carbonate. What is sodium carbonate? Na2CO3. Now, this is actually a really good one. actually don't like this. It is, but I don't like it. Let me explain it first. Here. Actually, you know what? No. We're cool. We're cool because it's not a solid. Guys, y'all listen for just a second. Remember earlier in fourth period when I told you all carbonates decompose into what? I need to make you very aware of this because I might have left this out and I don't remember. You need to make sure you know this. All solid carbonates. Okay, that's a very key distinction here because, read the question. It says a molar solution of iron is added to a molar solution of sodium carbonate. This is not a solid. What is this? This is aqueous. So what do we know? Is it going to produce a gas? It should not. Only solids are going to produce a gas. Well, let's read the question. Part A, do the molecular, the complete ionic, and the net ionic. So we're going to start with the molecular. This is the honors chem version. What type of reaction is this? Double replacement. So what is going to be one of your products? Let's start with what's on the first on the left, start on the right. Fe2CO3 3 plus NaBr. Very good. Now, one of these is really easy. What is NaBr's state? How do you know it's aqueous? Group 1. Get rid of it. Okay? Now, the one you may actually have to think about is, because we don't talk about carbonate very often, and I'll be honest with you, I don't even think I know what it is. But is that a solid or not? It is a precipitate? It's got to be. It's got to be. Just based on the question, the way it's asked. Because carbonates are insoluble unless with group 1s. I think we're gonna go to it. Okay? So I've just got my states of matter present. So let's go ahead and balance it. I've got one Fe on the left, two Fe's on the right, so give me a 2. I've got 6 Brs, I've got 1 Br, so that gives me a 6. And I've got 2 NAs, so I need 3, so this is your 2, 3, 6 rule. So you've got a 2, 3, 1, 6. 2, 3, 1, 6. Now, this is your honors chemistry version. This is not going to cut it. So the next part says write your complete ionic, which means you show everything in its ionic state. What is the only state of matter you'll ever see ions present in? Aqueous. How many aqueous things do we have up here? We've got 3 of them, so let's split it. So I've got Fe 2 plus Br minus. Hang on. Oh, my bad. 3 plus. Yep, sorry. 3 plus Na2 plus CO3 2 minus. Now, what do we write when it turns into a solid? We're splitting them into ions. What is a solid? What do? Write the solid. Don't break it. Fe2 CO3 3 plus, and then I've got more aqueous. So I've got Na plus Br minus. Say that again? Oh, okay. That's for acids and bases. If it's a strong, write the ion. If it's a weak, write the entire compound. I'm doing. This is the complete ionic. It asked you to do this. Now, here's the problem. Again, same thing works here. Do I have balanced atoms? No. What do? I need a 2 in front of the iron and a 3 in front of the carbonate. Now, remember the next thing is you got to make your charges balance. How many? Let's look at your total charge over here. I've got plus 6, I've got negative 1, I've got positive 2, and I've got negative 6. Wow, that was awful. My bad. Okay, now let's look at it. So what happens to all of your charges? All of them cancel out. We cool with that idea? Okay. Now finally, you need to write the net ionic. Is there anything up here that stayed the same? Na and Br. Sodium and bromide. So let's get rid of them. So all we have left is 2 Fe3 pluses plus 3 CO3 2 minuses and your solid Fe2 CO3 3. And that is your final net ionic. Does anyone have a question? You tell me? All right. What is this right here? It's a charge. What's this? What is this? That's -6. 3 times -2. You with me now? So +6, -6 cancel, leave you a neutral on both sides. Okay? All right, now, then it says find the limiting reactant. So here's what I'm going to do. I'm going to transfer this all to the next page. So I've got 2 Fe3 pluses plus 3 CO3 2 negatives gives me Fe2 CO3 3. Okay? Now, then it tells me there's a problem with this problem. There's not a volume. No, let's make both of them 500 milliliters. Yeah, well, okay. Just make it easier. That way you don't have to divide anything or multiply. All right, because all it gives you is concentration. It doesn't give you any volumes. It doesn't tell you how much of each one you have. So we're just going to assume 1 liter just to make it nice and simple. All right. So I've got 0.0540 molar, and I've got 0.0875 molar, and again I got 1 liter in each one of them. Now this is good for us, and we did make it a lot simpler because the next question is find the limiting reactant. What's that trick? Moles divided by coefficient. Very good. Now, how do you know the moles is already the molarity? Because molarity times volume is your number. What's wrong? I know. Yes, absolutely. Absolutely, you can. Okay. So we've got the moles of Fe3 plus is equal to 0.0540 moles. Now again, why is it the same as the concentration? The volume is 1. We're going to just assume 1 liter. I know it doesn't tell you, but we're assuming it. And then the moles of the carbonate is equal to 0.0875 moles. One more time. Why is the number of moles equal to the concentration? The volume is 1. Molarity times volume is moles. So the molarity times 1 is the same thing. Now what do you divide by? Coefficient, okay? What am I dividing the top one by? 2, the bottom one by 3. And remember, this is only going to tell you which one is which. That's it. That's all it's going to tell you is which one is which. Now, which one is going to be the least? Let's work it out. 0.054 divided by 2 gives me, I know, but I just want to show you the numbers. 0.027, the bottom was 0.0875. No, you have to show them. Nick, that is the one day on this planet that I need you to actually put some effort into your work. Exactly. Okay? So, it's close, but which one's the least? Okay? So that tells me, well, that this is my LR, and that tells me what about carbonate? This is your ER. So you just answered part 1 and 2, because 1 was what is the limiting reactant, 2, what is the excess reactant. All right, what's wrong? Go again. What's the difference? But why would you need the molecular to do this? We didn't need anything. Because it tells me specifically that the concentration of the iron 3 bromide is 0.054 molar. I understand that. But all we're trying to do is determine how many moles of the entire compound are present, which is 0.054 moles. You're overthinking it. I understand that. But I'm not trying to determine the number of moles of that other ion present. It doesn't matter. It's not affecting anything. Exactly, but that you don't need that here. Okay. I wish I knew of a way to explain this to you. It's not going to affect the. All right, but let me ask you this: if we did it back with this problem, with this part right here, is this the one you're asking about? If I did any of it, if I did it with that reaction, would any of my math change? No, my math would stay the exact same, because what did I do? I found the moles. I changed it from molarity to I tied molarity times volume, because do you agree that they tell you that the concentration of this is 0.054, and it is 1 liter? Whether it's this or that, do the numbers change? No. Over here, it's 0.0875 in 1 liter. None of the numbers changed. Did my coefficients even change? Nope. My math didn't change at all. So what you're actually doing is you're actually showing what's really even happening in this compound, or in this reaction. So, in fact, this and this have no effect on anything. Okay, so now we found our LR. Part 3 is the one I really kind of want to spend a little bit of time on, because we haven't talked a lot about this. And it says the concentration of the excess ions remaining. The first part. Yeah, well, first of all, we're good. The whole question is, what is the concentration? Yeah, no, part 2 is just carbonate. Yeah. The concentration of the excess ions remaining. Now, when it says remaining, is that before the reaction or after the reaction? It's after. That's the key piece of thing that I need you to keep in your brain as we're doing this. My first question is, do you agree that, what does the LR mean by definition? So do you agree that every single one of these moles are going to turn into 0? Yes. So I've got to have something left over. So my first objective is to find out how many moles of the excess would I use. Okay, so let's do that first. So I've got, I'm going to have to actually go back and look at it. I've got 0.0. Okay. So 0.054 moles of Fe3 plus. And I've got to convert it to moles of carbonate, right? Okay. So I've got moles of Fe3 plus, and I'm going to convert it to moles of CO3 2 minus. This is really easy. What is that over that? Yep, what is it? Should be 3 over 2. Okay? You've seen this before. All I'm doing is step 1, I'm converting LR to ER. That's what I'm doing. So 0.054 times 3 divided by 2 gives me 0.081 moles. And here's the key. And those of you that had me last year, you've seen this. That is how much was what? Used. Not left over. Used. So how do you find how much was left? Subtracted from what? Okay, so you have started with, this is kind of bringing back memories, minus used equals remaining. You should remember this. And what did you start with? 0.0875. 0.875. And we used how much? So 0.0065 moles remaining. This next part is the part that will mess everybody up. Because what was the question? And we never went this far last year. This is where we stopped. Very good, Nick. What he's saying is, remember, what was the question? The question said, what is the concentration? Remember, what is concentration? Moles over liters. I've got moles. I've got to get a volume. But the problem was, and I asked you this, when it said remaining, is that before the reaction or after the reaction? It's after. You took solution A and solution B, and you poured them together. So what would be your volume? 2 liters, not 1. So you've got beaker A, and you've got beaker B. And this is a liter, and this is a liter, and then you react them to get beaker AB. It can't be 1 liter, can it? It's got to be 2 liters. That's the part that messes everybody up every year, is they forget to add the volumes of the concentrations together. Yes, sir. Yes, ma'am. Sorry. That. We found the moles right here. So this is our number of moles. No. This is how many moles of carbonate would be left over after the reaction. That is still floating around in your in the product beaker. Just carbonate. Because remember, iron was the limiting. And what do we know about the limiting? It's gone. There's nothing left. Because remember, we're trying to find how much of the excess was left over. This is how many moles of the excess is left over. So then what you would do is you would take this and divide it by 2 liters. And that's how you know the concentration after the remaining. So the hardest part is adding your 2 volumes together at the very end. So just forget that every year. Which would be 0.0065. Yep. So, which would be 0.00325 molar. I'm even going to throw a bone at you, and you're not going to believe this. or this is the one you won't believe. It'd be millimolarity. I do hate it. Just to do it. But it should make sense, though. Milli is to the thousandth place. So times 10 to the negative 3 is the thousandth place. They would absolutely be impressed. They'd be like, oh, wow. Oh, wow. No. Listen to me. Because, remember, this was how much excess reactant was remaining. This next question says the mass of the precipitate produced. You got to get the product. Okay? So let's look at that. So let's go back. Now remember, so the last question is, how many grams of that stuff are we going to make? Well, which one am I going to pick? The iron or the carbonate? I've got to pick. Whoa. Hold on, Nelly. If we're cooking hamburgers, how many can I cook? Until something runs out, right? Well, I can't make just willy-nilly whatever I want. I've got a certain amount that I can make. And what's going to determine that? This thing, the limiting reactant. It says, what is the mass of the precipitate? Yes. I agree with that. I'm not. So what I'm asking you is, which reactant do we start with to convert to the precipitate? No. Well, I am. I don't need the carbonate for this question. I just need iron. Because carbonate is in excess. This isn't going to limit how much I can make. So, starting here. So I've got 0.054 moles of iron 3. So I'm going to moles of iron 3 plus moles of solid. And then I'm going from moles of the solid to what? Grams of the solid. This is part 4 of what, number 6? Or number 7? So this is just a straight Stoich problem. But the key is, you've got to start with a limiting reactant. Well, I'm going to tell you, the easy part is your mole to mole. And it's a 1 to 2. But the hard part is, and I don't feel like looking it up, would be whatever the mass is of that thing. Because it's significantly large. Because it would be 9 oxygens, 3 carbons, and 2 irons. And 1 iron is 55.85. I'm listening. Alright, the whole mass of this thing is 195.75. Yes, it is. Yes, it is. Oh, I see what I did wrong. I see what I did. Chill out. Hang on. It's 590. I added instead of multiplied. .9 grams. Sir. electrolytes conduct current in their solutions, which means they have to produce ions, which means it has to be a soluble salt, which means basically you know your solubility rules. If it dissolves, it's an electrolyte. That's your own fault if you don't know those. Yeah, yes, ma'am. Number 9. Okay. All right. Write the reaction equations. Now, I'm going to go ahead and say, screw the complete ionic. I'm just going to do molecular and net ionic. For the reaction between solid lithium carbonate and hydroiodic acid. This is actually a really good question, because there's something important in there, because it says a what kind of lithium carbonate? Solid lithium carbonate. Now, first of all, what would lithium carbonate be formula-wise? What's this formula, lithium carbonate? Li2, very good. Plus hydroiodic acid. Now, Hi, and it actually told you that in the problem, and we know that this is aqueous. Very good. It has to. I know, and this is one of those ones that are kind of challenging. So let me just go ahead and show you this, because what it's going to produce is it's going to produce lithium iodide plus carbon dioxide plus H2O. Because here's basically, I want you to think about this in your head. Imagine me handing you a white powder, and that white powder is not NaCl or sugar. It is lithium carbonate. And then I hand you a solution with a dropper bottle that's an acid. That acid just happens to be Hi. When you drop that acid on that solid, it's going to bubble. What's that bubble going to be? What kind of gas? Carbon dioxide. Also, what is going to happen to the water that was in the acidic solution? Because remember, if you think about this beaker-wise, if you've got H ions and you've got ions floating around, remember this is aqueous, right? So you've also got water present. So remember, you've also got lithium and you've got iodine present. When you drop that acid on this solid, is it going to dissolve? Yes, but here's the crazy part. What's actually going to take this solid and split it into its ions? The water is. The acid, the H and the I, have nothing to do with taking that solid and destroying it. The water is actually going to break it apart, because you got to remember, most acids are water, right? Well, the higher the concentration, the more hydronium ions you have. But most acids are comprised of water. So there's so much excess water in acid that the free water molecules that are not being a part of the hydrogen and iodide ion have the freedom to say, look, there's something I can eat, and it destroys this thing. So that is why you produce a liquid water and then this thing. But you got to remember, what do we know about all group 1s? They're soluble. So it's going to also split into its ions. So the key concept that makes this harder for students to understand, and this is why net ionics are so important, is that the way this looks, do you agree that it kind of looks like lithium and iodide actually form a bond and make a compound? That's actually completely and totally inaccurately true. So that's why we have net ionic equations, is to prove that lithium turns into an ion. But you got to remember, since this is already aqueous, how do we write it? We write it separate, right? Now notice, remember, cross out anything that doesn't change. This is a solid right here, right? So this doesn't change. So lithium went from a solid to what? So it's got to stay. Hydrogen went from its ion to what? Water. So it's got to stay. Iodine did what? Nothing. It was hanging out and got in the way. That is the net ionic for this reaction. So we have lithium carbonate. That's a great question. I'm so glad you asked this question. Plus H plus yields Li plus CO2 plus H2O. But that is a tough net ionic for students to understand because they don't see chemically what's happening in that beaker. Does this make sense, though? I feel like some of you weren't listening to that at all. All right. So imagine me handing you a white powder, and that white powder is Li2CO3. You're still not listening, and I'm explaining it again. Okay? And that white powder is Li2CO3. Do you agree that that would be considered a solid? Okay? And then I hand you a dropper bottle full of HI, which is hydroiodic acid. What are acids comprised of? Three things. Hydrogen ion, whatever the anion is, and water. Okay? So, when you take that dropper bottle and you drop that acid on that solid, what is actually technically tearing this solid apart? The water is. Because in acids, the higher concentration should be the water molecule. And there's enough free water molecules to come in. And are these things bonded together ionically? Water, the piranha, rips that solid apart. But the key here, Sarah, is, and you said this right, what do solid carbonates always produce? Carbon dioxide. No, anytime you, it doesn't necessarily have to be an acid. Anytime, that's something I'm going to have to look up and get back with you. That's combustion. I know all carbonates produce carbon dioxide. It doesn't have to produce water, and I don't know the exceptions to that rule. This one just happens to have to be water because of the acid. Okay, yes, ma'am. Let me finish this. So here's my question. So because this hydroiodic is an acid, it's aqueous. You have to split it, right? Well, my question when you kind of went was that when we write this in complete form, when we write Li, that looks and appears to make an actual chemical bond. But what's really happening in that beaker? Does Li and I get anywhere near each other? No, they don't. So why would we include this in the reaction when in actuality, this has never and will never make a chemical bond? This looks like they're actually communicating, but they're not. So if you split them into their ions because they're soluble, and you produce your carbon dioxide and you produce your liquid water, what do you notice about your iodine ions? They stay the same, so you get rid of them. So what you actually notice is that your lithium that's in your solid turns into a lithium iodine or ion. Your hydrogen ion turns into water because it's going to make a chemical bond with other things that are going on, and your carbon dioxide is also produced. So the iodine has no presence in this reaction other than watching it happen. So that's why we get rid of it. So that's the purpose of net ionics. Okay, yes, ma'am. A. Okay. D on 4. Can I do this one first since we're on it? Let me do this one first. We'll come back. I mean, I'm still talking about it. All right, so now we've got this. So here's the question. Medicines used to treat bipolar disorder are composed largely of lithium carbonate. If the tablet has a mass of 0.2 grams and 92.5 milligrams of gas are produced, my first question is, where would that even go up here? Carbon dioxide. My second question is, would you ever write down something in milligrams? No. So how many grams is that? 0.0925 grams. What percent of the medicine is composed of lithium carbonate? That sounds very familiar to this morning, doesn't it? Okay, so let's start with a simplistic question. What does this thing mean? Part over whole. So my question to you is, now do you notice the wording from earlier? The question we worked this morning said the principal ingredient was blah, blah, blah. This time it says that are composed largely of lithium carbonate, right? So is that entire compound, what's so funny? Screw the world! So we're trying to find the tablet and we're trying to find the lithium carbonate. Now, we're specifically working with mass, right? So this 0.2 grams is the tablet, right? So that is 0.200 grams. So this technically does not belong to lithium carbonate. It's only part of it. So your goal is to find the part that is lithium carbonate. Now, they've only given you one other piece of data about the chemical reaction. And what is that? The mass of carbon dioxide. So, Sarah, let me ask you this question. If I would have just given you this question right here, I have 0.0925 grams of carbon dioxide. How many grams of lithium carbonate do you have? Could you have answered that question? It's a three-step stoichiometric gram-to-gram problem. That's easy. The hard part about this question is A, knowing what a percent is, B, knowing how this percentage is defined, and C, knowing that 2 grams is the entire mass of the tablet. So if you go from gram to gram, whatever the answer is will go right there. Gram to gram. Yep. And remember, the key indicator of if you've done it right is the mass of the lithium carbonate has to be less than the entire mass of the tablet. That's the key. Okay? And really that's just like the problem we worked this morning. And so again, but you would multiply it by 100 and you would have your answer. Okay. Now you may answer your question. 4D. Now that I've thrown my paper. Oh. Alright. Determine the molarities of the following solution. Find the concentration of each ion. Shut up. Shut up. Alright, so here's why why I have not started this problem yet, is I'm thinking. Because the question says, determine the molarities for the following solutions. And this question says, find the concentration of each ion if 225 milliliters of 0.325 molar sodium nitrate are mixed with. Alright, I do know this. I can find the concentration of each ion prior to mixing. That's the easy part. So let's look at that. Let's start with the easy one first. So it says sodium nitrate, which is NaNO3, right? And it tells you that it is 0.325 molar, and I have 0.225 liters. This is that thing that Devin was talking about. What is the concentration of an ion in a solution? Remember, so if I want to know the concentration of the ion, it's the concentration of the solution times the subscript of the ion. Y'all should remember that. So, what is the concentration of the sodium ion? So what is the concentration of the sodium ion? What is the concentration of the solution times the subscript of the ion? It's the exact same. Why? You're multiplying it by 1. So what is the concentration of the nitrate ion? The exact same. No, there's no splitting. Well, let me ask you this. What you're wanting to do, in your math, you're wanting to add these two numbers to get the total. But let me ask you this. If I have NaNO3, for every NaNO3, how many NAs must I have? 1. How many NO3s must I have? 1. When I take them and I put them together, I have made 1 NaNO3. So if I removed an Na, then I've lost part of its concentration, right? But to create the entire compound, I have to have both of them. So the concentrations aren't additive. It can't have this concentration without either one of them. Did that make sense to anybody? James, explain it a little bit differently. Maybe they can understand if you say it. That doesn't help me any. Mary, did that make sense? All right, so let me see if I can do this way. I'm going to talk about this. Just listen. One Oreo is comprised of what? 2 cookies. Not 2 cookies. Two cookies. If I did this backwards, what if I started with MgCl2? You'd have 1 Mg, and you'd have, does it still yield 1 Oreo? Does that make a little bit of sense? Does that help? I don't know if that helps at all. But the concentrations aren't going to change. So if the concentration of this thing is 0.1, what's the concentration of the magnesium ion? 0.1. What's the concentration of the chloride ion? 0.2. Because if you go back and look, what is the ion concentration? It's the concentration of the solution times the concentration or times the subscript of the ion. Like I don't know of another way to explain this. Yeah, we've got 13 minutes left. I'm gonna fix and shut it down. Shut this down. Okay, well, let's do it. All right, so here's this first question. It says, what volume in milliliters is necessary to titrate the following bases using of 0.0125 molar hydrochloric acid. And then it gives you a hint. I'm going to be honest with you. The hint that they give you actually makes this problem harder than it has to be. They're wanting you to use Stoich, and I'm fixing to give you a formula to plug and chug. Yeah. Because what is that formula that you use when you have two molarities and two volumes and you're missing one of them? And it's an acid and a base. Not MS. MAVA equals MBVB. What's wrong with that? So this is all you need for that problem. They made it a little bit harder by telling you to use the stoichiometry, and in which you could, but let me kind of show you what I mean. What you could do, no joke, it's really difficult. Could you find the number of moles of this thing? Yes, you could find your moles of base, right? And then what you would do is you would go from moles of base to moles of acid. But the question was, define the volume. Well, do you have the concentration of your acid? Well, what is volume in your molarity formula? Remember, molarity is equal to moles over liters. Mole divided by molarity. How big of a pain in the butt would that be? So you would find your moles of your base, you would go mole to mole up to your acid, and you would plug the moles of acid in and divide it by this concentration. And that would give you your number of liters. That's stoichiometry. I'm sorry. That's much easier. Agree or disagree? I mean, really, that way works. You can do it that way, but I wouldn't do it that way. That's a lot more math. So it would be 0.0225 times 0.0335 divided by 0.0125. Now, Mary, be careful. What would that give you your answer in? This would give you your answer in liters, but what did the question say? In milliliters. So all you do is just multiply it times 1,000. Which, I don't know what that would be. And you do the exact same thing. Also, go ahead. Okay. Okay. I will tell you this, that, let me answer your question. In an acidic condition, whenever you have a redox reaction, sometimes you will produce a hydrogen ion as a part of the final chemical equation. In an acidic solution, that's okay. But in a basic solution, you cannot have them. I have not taught you how to convert it to basic yet. That will not be on this test. That will be in Electrum. So don't worry about number 12. You do not know how to do that one. Yes, sir. That you have to have a hydroxide in the basic solution. So just, and this will be the last problem I do, and we'll shut it down. So ox and raw, red, cat, oa. I didn't even write the reaction up here. P plus Cu2 plus goes to Cu plus H3PO4. And here's the interesting part. Did y'all notice that? It went from phosphorus solid to phosphoric acid. Okay. I don't know how that happened, but it did. So, the easy one is the copper. What did it go from into oxidation state wise? Went from 2 to neutral. So is that up or down? That's down, right? So you've got Cu2 plus going to Cu, and that leaves P going to phosphoric acid as your oxidation. And you can calculate and see what P changes to, but I'm going to guarantee you it's going to go up just because of where it is. Alright, so remember, atoms must balance first. P's balance? Yes. The problem is your O's don't balance. How do you balance oxygens? Out of water. How many to which side? 4 to the left. Now my H's don't balance. But here's the good thing. This is kind of one of those weird things. What people always want to do is come in and try to balance that H, but that would completely screw up everything. You would be doing this for the rest of your life, trying to make this balance if you put a number there, because that would mess up the P and the O, and you would go back here, and you'd come back here. So so don't put anything there. So how could you balance your H's? I have 8, but I've already got how many? 3. So how many do I need? I need 5 H's. You'd be shocked at how many people will spend hours trying to balance that and it would never work. Okay, so just come back in 5-8, add 5 H pluses. Down here, this one's good on atoms. So really the only thing that we need to add down here are what? 2 electrons. Now remember, this is reduction, so electrons go on the reactant side. So I need how many? My bad. I was going, but yeah, that's right. So 2 electrons there. Now, probably the one that's a little bit more challenging. But the good news is there's only one thing up there that's charged, and it's the hydrogen ion. So how many electrons do I need on the other side? I need 5. Okay, so again, remember I always do this. I have atoms, I've got charge, and then I've got electrons must be equal. We did the atoms, we did the charge. Now we've got to do the... Did we do charge? Yeah, okay, by adding the electrons. Yeah, that's right, okay? Now we need to balance the electrons. And this is lowest common multiple is to 10, right? So we can just come in and we can do a 2 up top. And we can do a 5 on the bottom. So that checks off. And again, the number one thing students forget to do is distribute those bracket values. So that is going to give us 8 waters plus 2 phosphorus plus, not yet, plus 5 copper 2 ions yields 2 phosphoric acids plus 10 hydrogen ions plus 5 copper solids. And that would be it. So to answer kind of your question, James, you said define acidic basic solutions. Because it said acidic, that thing right there would make it okay. But if the problem said it was basic, you could not have that. You would have to convert it to hydroxides, and I will show you that later, because it takes 2 more steps. And I don't want to show you all that yet. I want you to be confident in this, so when I get to this, you're like, oh, that was easy. Then I'll add 2 more to it. Everybody good on that? Pretty easy. Logan, you good? I like doing half reactions. It's challenging. You kind of got to think about it. Makes simple math seem really hard.